I just started it.
Okay, cool. Let me see. Let me see. For number 3C is false. I'm just confused on how it's false.
All right. It says the entropy of the system must increase in any spontaneous process. So when we're talking about for spontaneous and thus irreversible process, it says, right, the entropy change of the system and the surroundings must be positive. The entropy change of the system could be negative if the entropy change of the surroundings was large and positive, right? So think about how to describe this. You have let me try to think, well, what's the best way to go about describing this? My mind's not in entropy mode. I was just grading labs. Sorry, I'm trying to come back. All right, so we have, let me bring up this chart. Let me get my PowerPoint up. Oops. Let me get the PowerPoint.
Sorry about the hassle on this.
No, that's fine. I just need to get the right picture. If I get the right PowerPoint, then it'll make more sense. It's just taking a minute to open. Where is it? Just trying to find the right slide. Is well, from a mathematical perspective, I can describe it, but I'm trying to see if there's something better than a math. Because if you look at irreversible process, a really good picture. The only thing they're trying. There's not a really good picture of this in the slides. You know, the easiest way to understand it is, right, if you think of delta S of the universe is equal to, I mean, not equal, delta S of the universe is, yeah, I guess it is equal to the delta S of the system, oops, plus delta S, the surroundings, which is greater than 0 for an irreversible process. Right, for irreversible, I'm going to abbreviate. Which in an irreversible process is a spontaneous process, right? So what this is just trying to get at is, if you think about the entropy of the system, right? It's saying that in a spontaneous process, it has to increase. But from a mathematical perspective, if the entropy of the surroundings increases dramatically, then the entropy of the system does not have to increase. It's just the mathematical fact. And if you think about from trying to think of a system that would explain that. If we have a system here, and let me think, if we have little particles, right, and we, right, actually let me start here. Let's say we start here, we have a piston over here on the side, right, and if we look at the entropy of the system in a spontaneous process, if you have I'm trying to think of a spontaneous process that would, so so if we had this, I guess start vertically, right, and we had this piston up against the ground, and we placed a giant weight on top here, right? Gravity is going to push us down. That's going to be a spontaneous process. The system is going to compress, right, over time. The system will become compressed, and become more organized, and right, so the system is going negative, even though the surroundings, because the surroundings are becoming more disorganized because things are moving, and that disorder that happens, right, because you have external surrounding air filling in the space inside the piston, so it becomes more disorganized, even though the particles in the system are becoming more organized. That makes sense? It's a kind of a little bit more abstract thought, but it's all related to this mathematical equation right here.
So if it's constantly moving, then it's more disorganized.
So when something becomes more compressed, for example, it's going to become more organized, right? So this is going to be more when you compress something, and when you compress something, it becomes more organized because the particles are closer together. They have less room to move, so they have less. The number of the letter W. Remember the letter W. The number of microstates that exists for that gas. Those gas particles are less, and since they're less, the entropy in that system is going to be decreased. Whereas in a larger container, there's more space. They're going to be more. They have more microstates possible, so that entropy in this on the left is going to be more. But then when you have gas particles that are outside of the container, right? When you compress the piston, they're going to fill in the space here, and because this increases the amount of particle space that these particles can take up, the entropy of the surroundings increases. Even if it's just a small amount, it's going to increase. Does that make sense?
Yeah, that makes more sense now. I think we have a couple more questions. I don't know if Brian's got any questions right now, but For this is a simple question. Like for number 4B, do you have to I thought most things had to be in kilojoules. I was just curious, why is this one in joules, like the end product?
The only reason they went with joules is just because if it was in kilojoules, you would hurt, right? You just have 0.00234 kilojoules, right?
Yeah.
Oops, kilojoules, Kelvin. And that's the only reason they did it, is because the goal is always to try to have as few, zeros in your number as possible.
Okay. So, but for like the test,
it would have been fine. Either one is fine.
Okay, cool. I was just making sure. I didn't want to like mess that up on there. And so for number 5, this is also a simple one. So when you're finding Q, is Q usually found in like the book, like Appendix B or C or whatever? Is it Q always gonna be found in there?
The delta H of vaporizations you can look up in a table. So these you can look up in a table, yes, and they are directly related to Q, right? So.
Okay, and is that for like most things, like when they do involve Q, like most equations?
Yes.
Okay, I was just making sure there too. Another one we're kind of confused on is also number 5B for like the microstates. We're just kind of confused on the difference between like the higher temperature and the lower temperature.
That's still part of this. All right, so the amount of, let me try to think of, if you think about your vaporization process, you have, trying to think of how to describe this. You have your container, right? And there are 2 containers. Right? One has 25-degree water, the other one has 100-degree water. Does it make sense, first of all, that the particles on the right container are going to be moving a lot faster, right? Whereas the ones on the left are going to be moving slower. Does that make sense? Just because of temperature?
Yeah, that one makes sense, yeah.
So from an entropy perspective or from an energy perspective, there's more movement occurring in the left container than there is in the right container. So when you're vaporizing, because these molecules, even though there's they're not boiling, they can still vaporize in both cases, right? At 100 degrees, you're at the boiling point, so they're easy to vaporize because you have enough energy to enter into that state, into the vapor. But at 25 degrees, you have less particles that are able to vaporize. So you're going from a more organized state, right? Because the reason that you're able to vaporize these molecules is you have water molecules, right? And they're forming hydrogen bonds with neighboring water molecules. Okay, so there's an interaction here of some forming hydrogen bonds that exist between water molecules. And as you heat the system up, these hydrogen bonds begin to break. So the higher the temperature, the less hydrogen bonds that exist between the molecules. And hydrogen bonds are ordered. So at 25 degrees, you have more hydrogen bonds, so you have more order in your system. At 100 degrees, you have less hydrogen bonds, so you have less order in your system. So you're already starting from a higher delta, higher state of disorder when you're at 100 degrees. So to go from, I'm just trying to think if you have a an S chart, right? At 25 degrees Celsius, you're going to have a more ordered system. At 100 degrees, right, you're going to be at a higher energy state. If you need to be, from a disorder perspective, you need to be up here somewhere for total vaporization, right? You have to become much more disorganized here than you do there. Does that make sense from that perspective?
Yeah,
because you need to have a lot more disorder occurring in order to vaporize starting at 25, because it's more ordered. I mean, if you think about it from the perspective, if you started from an ice cube, right? If you had an ice cube, everything is very, very organized. And then you become a liquid where it's a little more disorganized, and then you go to a vapor. So you have this kind of gradual transition as you increase temperatures. So the number of microstates that are available when you have, from a microstate perspective, the hydrogen bonds that exist in the lower temperature system are less, because the hydrogen bonds don't let the water molecules move very freely, whereas at the higher temperature system, the interactions between the molecules are less, so you have more microstates available to you.
Okay. So for a microstate, that's like, I just want to refresh my memory. So it's like sort of like taking a picture of the whole like reaction, like saying they got a still point and something like that. Just sort of like a microstate.
Yeah. So microstates, like, let's just, you have the 25 degree system and let's just say there were only two molecules. At a microstate, you'd have, at 25 degrees, you'd have one with the two molecules there, another one with the two molecules there. You'd have another one with two molecules up here, right? The number of microstates is just basically the number of snapshots of the different positions, vibrations, etc., that exist for a system. And you have more of them or less of them depending on, in this case, the number that you have, here. And then, right, a vapor has lots and lots of microstates because it's not limited by the shape of a container, right? So you have lots of microstates available, and that's going to be, up here, right? From a microstate perspective, we have lots of microstates available for complete vapors, whereas the hot water, the 100-degree water, because these molecules are flowing freely past each other, there's just a lot more microstates available to them. So they're already starting at a higher level of microstates, right? Whereas the colder water has less, because the hydrogen bonds are still there, you have to overcome those, get to that more microstates so you can then jump into the full vaporization.
Okay, yeah, I just wanted to refresh my memory on that, and I apologize.
Yeah, you're fine.
And for number 6, I pretty much understand most of this, but I just have a couple of questions. So if so say they're both the same, like both substances are the same, but like the grams of each, like number D, if to say the grams are different but everything else is the same, the one that's higher, is that the one with the more entropy?
Repeat that.
Like for say they're both solids or aqueous, what if one has more grams than the other, would the one with the more grams, do they have the larger entropy?
Correct. Yes.
Okay, I just wanted to make sure that. And then the same thing with temperature too, if whoever has the larger temperature has the more entropy.
Correct.
Okay, cool. I don't know if Brian has any more questions.
If he's been adding to the text box, I can't see it. So.
Okay.
Oh yeah, I had like questions on the later problems, but I don't know if you have any more questions. Like, I have questions on like I think number 11, just like knowing how to come up with these balancing equations, or Just the equations, I mean, in general. I think it was 11 or 12. Oh yeah, 12.
Oh, okay.
Sorry. I think, yeah, it was A.
Okay.
So, yeah, I was just having trouble, like, it says write the chemical equation for the equilibrium that corresponds to Kb. So, like, where would I start with that? I would just start with the CH3 and H2, and then
Yeah.
I would just know to add H2O.
So this is the one thing you would need to learn. This is the reason I actually put this in the problem set is, for the most part, most of the things that we work with, right, are, we've seen over and over again, you have acid, right, where you have something that's going to react, and you have something that's, basically going to produce an acid. This is one of the cases where it's, if you think back to NH3 for ammonia, right, the reaction of ammonia, when you dissolve ammonia in water, this is one of the bases that exist. Ammonia reacts with water to form an equilibrium, right, with water to form the ammonium ion plus hydroxide ions, right? And this is a base. And this problem is just meant to show and signify that, when you have CH3 and H2, all we did was replace one of the hydrogens here with a CH3. So this problem is exactly the same as ammonia. The only difference is one of the hydrogens has been replaced. So you need to be able to recognize bases. Oops. You need to be able to recognize that bases have this particular path available to them. And so that's the first thing. So you'd have to recognize that, right, you're making the H2O. And again, you form an equilibrium to give the CH3 and H3 plus. All we're doing is, again, we just replaced one of the hydrogens here with the CH3. If you think about from a structural perspective, what this looks like, this is right. You have an H3, just looks, it just looks just like that. The only difference is instead we have a CH3 down here. It's the exact same thing. So, and these are, when you react bases with water, they form hydroxide ions. And this is the reason they are bases, is because the OH, or the HO minus, OH minus, however you want to draw it out, is a base, right? And this is, what we're thinking about the chemical reaction. And hence, that's why you have a Kb associated with it, is because you're, producing a base.
Oh, okay. Yeah, that makes more sense. So it'd be like your conjugate base, conjugate acid, right? If I remember correctly.
In this case, yeah, you have a base and its conjugate acid, and then and then water is the acid, and OH minus is the conjugate base in this case.
Okay, got it. Thank you.
Yeah. Okay.
I think that might be it. I don't think I have any more questions. No, I don't see any more questions I got.
All right.
I don't know if Brian's got any more.
Sorry, I'm just looking.
No problem.
No, I don't think. Oh, so for part B on 12, we say 8.314 times 10 to the negative 3. Is that just because we're using kilojoules?
Yeah, this is just the constant R for.
Okay, got it.
There, R exists in multiple different forms, and this is the one that allows you to cancel out temperature and.
Okay, got it. Just making sure.
Yeah.
Yeah, I think that's it.
So, but when you're trying to find G, is it always going to be in kilojoules, or again that it doesn't really matter?
It just depends on the number. It doesn't make a difference, whichever one makes the most sense, either kilojoules or joules. It's just, you want to make sure the 8.314 is going to be in the kilojoules, which is why you end up with kilojoules out in the end here. But
Okay.
as long as you get the right one out in the end, you'll be fine.
Okay, so it doesn't 100% matter which one we end with, it just is the right number, or you want it to be like the right exactly thing.
You'll be fine with either.
Okay, sorry about that.
Yeah, no problem.
But no, I think that's it for my questions.
Yeah, same.
Okay.
All right, thank you.
You're welcome.
Oh, and are you going to start our exam at 8:15 or 8:50?
You originally had said 8:15, so I set it for 8:15.
Okay.
I can change it if you needed to, but
No, that's fine.
okay.
Yeah, I'm fine with that.
All right.
All right, thank you.
All right, thank you so much.
All right. Good luck, guys.
Thank you. Bye.
Bye.
Bye.